in the summer that we're able to see because of Claire's work.
After we had a record that was about 15, 20 years long, we started noticing that the extent of the ice in the Arctic was getting smaller over time.
Sea ice is formed on the surface of the ocean and therefore is made from seawater. The biggest concentration is in the Arctic, and it's also where the biggest loss in sea ice is occurring. Every year, NASA reports on the sea ice minimum and maximum extents. As expected, the data is concerning.
By now, not only has this trend toward lesser ice continued, but it's even accelerated, so that now the decreases are greater than what they had been.
These trends are deeply troubling, but one thing's for sure. Our awareness of shrinking sea ice extent due to climate change was propelled faster and further after Claire Parkinson arrived at NASA.
I mean, she takes her job seriously, and the health and welfare of those instruments in space, yeah, she's on it. You know, it's one of the things you don't worry about because Claire's in the loop on these things. It's going to be fine.
In science, we stand on the shoulders of giants, on the shoulders of those who explored before us. But then, some among us are giants.
Tuesday was cold, I almost froze my toes. Oh, what's it gonna be next week? Who knows? That's climate. Oh, that's the climate you got. You take a bunch of weather and you average it together and you're doing the climate rock.
At a glacial pace, it means something's happening so slowly you can barely tell it's happening at all. That used to describe the very incremental movement glaciers and ice sheets experienced each year. But now that's changing. We're tagging along with 3 NASA scientists to understand the different lengths they go to not only investigate ice sheets and glaciers, but also communicate their often complicated science to the public. First, let's get oriented. Ice sheets, in pink, pretty much occur in only 2 places, Antarctica and Greenland. Glaciers, in yellow, play a key role draining melt off the ice sheet. Glaciers are also found in the high mountains, but we'll get to those in another episode.
So we know that something's happening in Greenland right now that's unprecedented in the last several thousand years.
That's Dr. Josh Willis, oceanographer at the Jet Propulsion Laboratory. Josh and his team are tackling one of the major environmental challenges of the 21st century, trying to answer fundamental questions about how melting glaciers impact sea level rise.
With my mission, Oceans Melting Greenland, or OMG for short, we're trying to understand just how much of Greenland's melt is caused by the oceans.
Along with being one of NASA's top scientists working on the cryosphere, Josh is passionate about demystifying climate change in typically unconventional ways.
I think by reaching out to people with a little bit of humor, a little bit of fun, maybe a song, you really have the opportunity to help people understand and come to terms with what we're doing to our planet. Because it's definitely happening and it's definitely a big deal, and we need to start preparing for it.
Down at the opposite pole, Dr. Kelly Brunt is getting ready for a major expedition.
In December and January this coming year, I'll actually be in Antarctica down near the South Pole collecting ground-based GPS data.
This is actually Kelly's second expedition to the South Pole. The first occurred in December and January of last year. Both surveys are critical and will help validate data collected by NASA's airborne campaign, Operation Icebridge, and the recently launched satellite mission ICESat-2.
All 3 of these layers, that ground-based, that airborne, and the satellite, are all tied together. The ground-based helps validate both the satellite and the airborne the airborne helps give us more validation data for the satellites, but also a bigger story with respect to the depth of the ice sheet and what's going on underneath the surface.
While some scientists are taking measurements in the field, others are looking for answers in physics and lines of code.
For me, the projections that we are doing, they do have a very personal meaning.
Dr. Sophie Nowicki is an ice sheet modeler. That means she and her team have the important job of forecasting how ice will change in the future, which also predicts changes in sea level rise. It's a job she doesn't take lightly, especially since urban planning and infrastructure use her team's models to make decisions about the future and safety of their communities.
When we make those projections that are 100 years in the future, 100 years can seem so far away, like I don't have to worry about it, it's just too far. But actually they are not. It's really like the future that we are looking at that our children or grandchildren will see to experience.
Whether it's learning to communicate in new ways, traversing a swath of Antarctica in a massive piston bully, or taking responsibility for an impactful climate forecast, our NASA explorers are pushing the limits of discovery every day. But on a very human level, they're people with families and friends who have a stake in finding out why and how the planet is changing as rapidly as it is.
Some places on the surface you might have these steep cracks and giant fissures that you would have to be careful not to fall into. In other places you might see towers of ice right next to places that were relatively smooth. You might see places that were dark. Ice there takes the form of rock. It's frozen solid until you dig down into that ocean. So you may see some things that look similar to Earth, but you may see some things that are very different.
That voice you just heard?
I am Morgan Caymore, NASA scientist.
I love it. That's Morgan. She's probably one of NASA's best spokespeople for exploring our solar system's icy moons.
Europa is a fascinating place. It has this liquid water ocean that's about 3 times the volume of all of Earth's oceans combined. That's a lot of water.
To understand what makes Earth so special, sometimes you need to back up and take in the big picture. Remember, the cryosphere is every place on Earth with frozen water. And water is one of the biggest indicators for life.
Every place, at least so far, that we have found life, we found water along with it.
And so far, Earth is the only planet we know of with life. Although Europa isn't the only icy moon in our solar system, NASA has identified it as one of those places with key astrobiological potential. Morgan is a collaborator on the Mapping Imaging Spectrometer for Europa, an instrument selected for NASA's next mission to Jupiter's icy moon Europa. But she's also more than just a scientist working in a laboratory. She's preparing future NASA missions for success on the surface of alien worlds. This year, Morgan and her colleagues were in the field studying how life colonizes in fresh lava.
Earth, it turns out, has a lot of excellent, what we call analog environments, places that are similar enough to some of these other worlds that we can conduct some tests and we can do some analyses here. Now, they're not perfect, of course. They're not going to be exactly like Europa, but we can still learn a lot by testing in these environments. Some of these places include Antarctica and the Arctic Circle, but there are other places too, Alaska, Greenland, even Iceland. Any place where you have a lot of ice, because guess what the surface of Europa is made of? A lot of ice.
Studying the cryosphere doesn't just have big implications for Earth. It also matters for the frozen worlds in our own cosmic backyard.
If we're able to find life or evidence of past life on a place like Europa, that tells us that not only can life happen in other places, but it's common enough that it happened at least twice in the same tiny solar system. That means that the universe is wide open in terms of how much life we might find, the types of life we might find. It would revolutionize how we see ourselves and the possibilities for contact in the universe. It would be amazing. Oh, it's so exciting.
My interest in glaciers comes from the sheer size of these things and how much they're able to change on human timescales. And so the amount of mass and energy being transferred by glaciers around the globe is tremendous. It's an absolutely fascinating thing to study from space.
Mountain glaciers are some of the most charismatic parts of the cryosphere. Some might cling to the edges of cliffs at higher elevations, then lay bare and flat in a broad plain, looking cracked and weathered like elephant skin, before tumbling thousands of feet toward the sea and terminating in a dramatic calving front. They're like motion frozen in time, until they aren't. They tell a story about the distant past and yet are incredibly responsive to the present. You can understand why they'd be captivating to all of us, and especially cryospheric scientists. Meet Alex Gardner, a cryospheric scientist at NASA's Jet Propulsion Laboratory, who is going to help break down what a classic West Coast North American glacier might look like, where high amounts of snow dump onto the mountains.
And at higher elevations, there's melt in summer, but not enough melt to get rid of all of that snow. And so that snow accumulates, it compacts, it turns into ice, and it starts to flow under its own weight, and it flows down the valleys. And as it flows down the valleys, it actually carves those valleys out and it makes them deeper. And so it creates these beautiful fjords where the ice flows down, snakes out and down to the ocean or to the lakes or further inland. And so that ice is flowing, it's moving.
Alex uses satellite data to study large-scale changes in glacial ice. But 2,000 miles to the north, Chris Larson from the University of Alaska Fairbanks spends a lot of time studying glaciers from the air. He's been flying over Alaskan mountain glaciers for many years, most recently on a NASA-funded mission called Operation Icebridge Alaska. He's absolutely enamored with his local rivers of ice.
And what do you love about mountain glaciers?
Well, they're in mountains, so they're really pretty.
You couldn't ask for a better way to experience Alaska on a large scale than to go flying around for campaign after campaign and look at all of the mountains in Alaska. Truly infinite. You just feel like you'll never see the end of them and don't want to either.
But Chris doesn't spend weeks away from home and family
go
for the
around
views.
for
Chris and his
campaign
colleagues at
campaign and
NASA
look at
want to answer
all
some
of the
pretty big
mountains in
questions
Alaska.
by learning
Truly
more about
infinite. You
Alaskan
just,
glaciers and
feel
how they
like
tick.
You'll never see the end
why
of
does
them and
NASA
don't
care
want to
about
either.
these?
Well, they actually
But Chris doesn't
disproportionately
spend
contribute a
weeks
large
about Alaskan glaciers, Greenland and Antarctica,
never see
stand
the end
to
of them.
contribute the
NASA
most
care
to
about
sea level
these.
rise,
Well, they
simply
actually
because Chris hasn't
disproportionately
been
contribute a
weeks
large
since ice is stored there. But currently, it's the world's smaller mountain glaciers in comparatively warmer places, like Alaskan glaciers, Greenland and Antarctica,
about
that
the
contribute the
NASA
most
care
to
about
sea level
these. Well,
rise,
they
simply
actually
because Chris hasn't
disproportionately
been
contribute.
1% of the world's ice.
Mostly due to them being dynamic. They have water at the bed, which allows them to slide fast, and they react quickly to climate change and have higher velocities than their polar counterparts.
Back at JPL, Alex uses satellite measurements of global ice and computer models to predict ultimately how much sea level rise we might see due to climate change. But in the case of mountain glaciers, we also care about the local impacts of disappearing ice.
When we think of changes in ice sheets, we typically think of just what is the consequence for sea level rise and the future evolution of the ice sheets. But glaciers in other regions, like high mountain Asia, Alaska, the European Alps, These are places where changes in runoff matters to stream flows. In places like high mountain Asia, you have a lot of glaciers that feed the streams that flow down to populated regions. And that runoff becomes significant for water resources, irrigation, and agriculture.
Both Alex and Chris are passionate about understanding how glaciers are changing and what it means for our planet's future. They'll continue to use tools like elevation maps from the ICESat-2 satellite and detailed airborne measurements to monitor changing ice.
What we're looking at is a legacy of the Ice Age. Permafrost and methane is a time machine. So what we're going to do is walk back in time. We're going to see old carbon, old bones, old environments, and none of those are in equilibrium with today's climate, so that's the problem. That world doesn't exist anymore, and it hasn't for 10,000 years. It was nicely and very delicately separated from this modern warmer climate by about this much moss. And when that moss goes away, whether for fire or for human
In this video,
disturbance,
we'll walk you through how to use
warming,
YouTube Slide.
then all hell breaks loose.
Permafrost. It's maybe the part of the cryosphere that's most out of sight and mind. It's fascinating how it formed in the first place and how it got loaded with so much carbon. In a minute, we'll go back underground with Matthew Sturm from the University of Alaska Fairbanks. But first, let's meet Peter Griffith, NASA's project manager for the Above campaign, which supports more than 70 science projects studying forest and tundra vegetation, wildfires, animals like birds, caribou, and Dall sheep, methane emissions from expanding northern lakes, and the impacts of climate change on people in Alaska, Canada, and around the world. Many of those projects have some direct connection to permafrost.
Permafrost is the hidden cryosphere. It's the permanently frozen soil that surrounds the Arctic, all across Alaska, northern Canada, and then across Eurasia. The ground has been frozen during the ice ages.
During the ice ages, there was not enough snowfall in the drier regions of Alaska and Canada to form glaciers there, so the land was suitable for vegetation.
What happened is that over thousands and thousands of years, all of that plant material got compacted and frozen every winter and buried and pushed down, so that today there's 300 feet deep of frozen water and dead plants and some pieces of dead animals too. Sometimes you find woolly mammoths in the permafrost. But most of it, of the organic matter as we call it in the permafrost, is frozen plant material.
Some of that plant material is now thawing and decaying, releasing its ancient carbon into the atmosphere, sometimes in the form of methane gas bubbling out of expanding northern lakes.
We started this field campaign because the Arctic is the part of the planet that is warming first and fastest. And there are consequences to this for permafrost. So during the Arctic Boreal Vulnerability Experiment, we're studying permafrost with people on the ground, from aircraft flying over the region, and also from satellites in space.
Another way to understand the permafrost is to take a walk below ground with Matthew Sturm and into the U.S. Army Corps of Engineers permafrost tunnel.
And they've dug this tunnel back into the side of a hill about 200 feet, and it goes sort of sloping down so that by the end of the tunnel you're about 100 feet underground, and you're surrounded by bones sticking out of the wall from the steppe bison and mastodons that are frozen in it. There's sticks that are 40,000 years old, that you can touch with your hand. There's grass that's still green that's tens of thousands of years old because it got frozen, right away, and it's never lost the green color.
But as fascinating as it is to see these relics of an ancient era, or to see a tree split in half by thawing soil, or even to light a ball of methane on fire from under winter ice, at the end of the day, Peter and his colleagues want to know just how much organic matter is frozen in that permafrost, and how fast it might be released.
Currently, we think that there is something on the order of 2 to 3 times as much carbon locked up as frozen organic matter in permafrost as there is carbon dioxide in the atmosphere. So, releasing all of that organic carbon from permafrost into the atmosphere would be a real game changer. That would be a tremendous transformation of the planet's atmosphere. Now, the good news is that it would take a very, very long time for that to happen. However, we are warming the planet at a rate now that calls into question how quickly is that changing and what the consequences in the near future and in the far future are going to be.
We're at Vandenberg Air Force Base for about 20 minutes before the launch of ICESat-2. You might see the white light off in the distance. That's the Delta II rocket.
It kind of feels like an idea that was always going to just stay an idea. But no, it's real. It's sitting on top of the rocket.
For me, it's kind of surreal. Like you say, it's been 10 years. It's hard to believe. It's like, we're really here? This is really about to happen? It's totally cool.
This is Dr. Tom Newman. Over the years, his work has taken him to some pretty remote areas to study changes in the ice regions of our planet. And his research, among many others, has defined the goals of the new NASA satellite, the Ice, Cloud, and Land Elevation Satellite 2, or ICESat-2.
The story of ICESat-2 really begins with ICESat-1. ICESat told us all kinds of cool things about the ice sheet and about sea ice that we didn't really know to ask. That data allowed us to measure elevation change of ice sheets in a way that we hadn't been able to before, and showed that all the action on the ice sheets, the places that were really changing quickly, were around the edges. So when we were thinking about what could we do better next time, we knew that was one key component.
In addition to the edges of the ice sheets, ICESat-2 needed to measure a dimension of sea ice that remained elusive, its thickness. To figure out how thick sea ice is, you can measure the height of ice sticking out of the ocean, or freeboard, and compare it to the height of water between the sea ice flows, called leads.
The problem is, sea ice is really dynamic, and those cracks open and close various places in the ice pack throughout the day, throughout the year, and what we need to do is have measurements of the ocean whenever it's available, wherever it occurs in the sea ice pack.
To solve that problem, ICESat-2 was designed with a fast-pulsing laser instrument to take precise, near-continuous measurements across its 3 pairs of beams. For 10 years, everything about the mission was designed to measure rapid changes in the most rapidly changing part of the cryosphere. But it has to get into space first.
But it's a huge transition going from the ground to in space. We've spent better part of 10 years, thousands of people have been involved, and actually seeing the rocket there on the pad with all of that work kind of all put together in one place, it's pretty amazing. And then getting up in the middle of the night to go watch the actual launch, it's sort of surreal in a way, because you've put so much time into it for so long, and actually seeing it over there, it's like, whoa, it's a big deal.
Star 2, 1, 0, liftoff, +1. বিশেষ বিমানবন্দরে ফিরে আসছেন শ্রমিকেরা গত 4 মাস ধরে প্রতিদিন এই হার বেড়ে চলেছে, কিন্তু হওয়ার কথা ছিল উল্টো বছরের এই সময় শ্রমিকদের সেভাবে পৌঁছে দেওয়ার ব্যবস্থা করা হয়। গত 9 মাস ধরে
That was awesome. Totally cool. There it went.
এই অবস্থায়
That was
বাজারে
Atlas.
হাত পেতে চলতে হচ্ছে
Last Delta II had not out.
তাই মানবিক সহযোগিতা পাওয়ার আশায় প্রতিদিন সকালে ভিড় করছে।
So Atlas has been turned on over the course of the first few weeks of the mission, really culminating for us with the laser. So this is our first look at sea ice data from ICESat-2, and it looks fantastic. The signal levels look great. We've got plenty of photons there. We're capturing ridges. We can clearly see the ocean. All sorts of cool stuff in there, and this is just our first data. It's only going to get better from here on out.
The data from ICESat-2 is well on its way into digging deeper into the unknown dimensions of sea ice sheets, and glaciers. It will shed light on changes in sea level and global weather patterns, and once again find new things about ice we didn't know to ask.
So my heart is definitely racing. I don't know about anyone else's. This is the stuff nerds dream of.
10 seconds. 9, 8, 7, 6, 5, 4, 3,
করোনা ভাইরাসের কারণে বাংলাদেশ সহ 25 দেশের আটকে পড়া প্রবাসীরা আবারও সৌদি আরবে কর্মসূচি করার সুযোগ পাচ্ছেন। কিছু সিভিল এভিয়েশন কর্তৃপক্ষ এদের পরিস্থিতি বের দেওয়া না হলেও যাওয়ার কার্যক্রম এই তালিকায় নেই ভারত।
That countdown you just heard? We'll get back to that in a minute. Last episode, we saw the epic launch of ICESat-2, NASA's newest state-of-the-art ice-observing satellite. But now that that's in orbit, the pressure to deliver results is on.
Between launch and, the first ground returns, it took 17, 18 days or something like this. It's a time when you're quite nervous.
9 years ago, Dr. Torsten Marcus took over as the lead project scientist for ICESat-2 during a time when the mission needed a champion.
You start fighting for a mission over, for 9 years now.
So when ICESat-2 was turned on for the first time 18 days after it was launched, only then would the science team know if the whole thing had worked. And it did. If it sounds like there's a lot of noise in the background, that's because Torsten is being interviewed from a plane 1,500 feet in the air. IceBridge was tasked with the job of bridging the data between the end of ICESat's mission and the beginning of ICESat. If it sounds like there's a lot of about a 9-year difference, that's because Torsten is
the goal is that it would run until ICESat-2 launched and then would have overlap with ICESat-2 as well, so we can get a really long, well-calibrated
ICESat's mission
from IceBridge.
As the deputy project scientist for Operation IceBridge, Brick works closely with Torsten to make sure the two missions are syncing up.
The timing was everything during that mission, which was a real challenge because not only do we need to...
Basically what you need to take away is getting an airplane and a satellite in space to fly over the same flight path at the same time and collect...
সাদা পাথর রাতার গুলেও একই অবস্থা এতে দেশের বিভিন্ন প্রান্তের ভ্রমণকারীরা হতাশ
অনেক দূর থেকে আসছিলাম কিন্তু এখানে এসে শুনতেছি 5.5 মাস ধরে এখানে নিষেধাজ্ঞা চলতেছে
নিষেধাজ্ঞা থাকাতে আমরা ভালোভাবে সেটা দেখতে পারতেছি না
পর্যটক না আসায় মানবেতর জীবনযাপন করছে এই শিল্পের সাথে জড়িতরা
150 ফটোগ্রাফারের মধ্যে কেউ ছবি তুলতে পায় না খুব কষ্ট দিয়ে দিন যাচ্ছে আর কি
ব্যবসার অবস্থা এখন খুবই খারাপ এই আমরা দোকান বন্ধ রাখি ভাড়া দিতেছি
তাদের বিকল্প কোনো কর্মসংস্থান নেই এতে করে পর্যটন কেন্দ্র খুলে না দেওয়ায় এই যে প্রান্তিক জনগোষ্ঠী তারা না খেয়ে জীবনযাপন করছে
করোনা সংক্রমণ রোধে বন্ধ পর্যটন কেন্দ্র হোটেল
অবস্থা এখন খুবই খারাপ আমরা দোকান বন্ধ রাখি ভাড়া দিতেছি
তাদের বিকল্প কোনো কর্মসংস্থান নেই এতে করে পর্যটন কেন্দ্র খুলে না দেওয়ায় এই যে প্রান্তিক জনগোষ্ঠী তারা না খেয়ে জীবনযাপন করছে
করোনা সংক্রমণ রোধে বন্ধ পর্যটন কেন্দ্র
হয়ে আমাদের দোকান বন্ধ রাখি ভাড়া দিতেছি তাদের বিকল্প কোনো কর্মসংস্থান নেই এতে করে পর্যটন কেন্দ্র খুলে না দেওয়ায় এই যে প্রান্তিক জনগোষ্ঠী তারা না খেয়ে জীবনযাপন করছে
করোনা সংক্রমণ রোধে বন্ধ পর্যটন কেন্দ্র হয়ে
দোকান বন্ধ রাখি ভাড়া দিতেছি তাদের বিকল্প কোনো কর্মসংস্থান নেই এতে করে পর্যটন কেন্দ্র খুলে না দেওয়ায় এই যে প্রান্তিক জনগোষ্ঠী তারা না খেয়ে জীবনযাপন করছে
করোনা সংক্রমণ রোধে বন্ধ পর্যটন কেন্দ্র হয়ে
দোকান বন্ধ রাখি ভাড়া দিতেছি তাদের বিকল্প কোনো কর্মসংস্থান নেই এতে করে পর্যটন কেন্দ্র খুলে না দেওয়ায় এই যে প্রান্তিক জনগোষ্ঠী তারা না খেয়ে জীবনযাপন করছে
করোনা সংক্রমণ রোধে বন্ধ পর্যটন কেন্দ্র
মৌসুমে প্রচুর লাভ